Hello, everyone. Welcome back. And I know some of us are losing our voices a little bit, this dry air, but I hope you all have had so far a great morning. I want to say something. When you go into at the coffee breaks, please stop by the Innovate booths. We're going to try something going forward where we, this year it's ServiceNow, Noblesse, and Veritone, is we work with them on the publication of not so much a commercial, but what's the problem that you solve? And who do you solve it with? And then we have an electronic distribution of it, and it's for our CES government attendees, and they all have booths in there. And this was an initial year with initial pilot, and we're gonna go forward with it, we think. And we want it to be a continuous communication mechanism, Innovate, that is integrated with the with CES. And by the way, people think of that as the Consumer Electronics Show. It's not. They bristle when it's called that. It is CES because a phone is not a phone. A television is more than a television. A tablet isn't something you use a pen and a pencil with. Well, it is, the electronic ones now. But it's the integration of business and government systems. And this program intersects with pavilions they have on smart cities, transportation, cybersecurity. And so increasingly, we're doing that integration going forward. Our next speaker is, in addition to artificial intelligence, one of the technologies that people forecast to have a significant impact is quantum computing. And what we see is a debate going on, is it real, is it not real? Our next speaker is the CEO of DWave. It's a company that actually has, I may be wrong on the number, but I believe 5 quantum computers in production. Now, I'm not as technical as many of the people in this room, but when I hear numbers like 100 million times faster than what's today, I can't get my head around what that means. But is it real or not real? You can sometimes tell by the people who are the leading companies that are in that space. And if it wasn't real, I don't think a man like Ewald would be leading it. When I looked at his resume, and we've talked a few times over the past several months, if at different points in his career, he was president and CEO of 3 companies that you'll all know, Linux, Silicon Graphics, and Cray Supercomputing. So he has a background in this industry. He's been in all of his career. He was going to be here with Tom Soderstrom, who obviously is a victim of the government shutdown. And I've gotten 4 texts from him. Can I video in? Can I pipe in? But we just weren't able to do that. Tom and Bo will be meeting with us in Washington in one of our programs in the next, actually late spring. But please welcome to the stage. You're really going to enjoy this presentation. He went from sharing 20 minutes to having it all. Please welcome Bo Ewald. I keep thinking they're coming from behind me.
Thank you. Well, thanks for coming back from the break. We're going to talk a little bit about quantum computing, and I brought some quantum stuff with me. It's cleverly disguised as cans of corned beef hash. But we'll get to that in just a second. So, and don't let me forget it, that it's there. It might go to a different universe. So really pleased to be here. Thanks, Don. This will be great. And so sorry, Tom, if you're listening in about how goofed up things have gotten. But we'll talk about kind of 5 major areas, and then I'm going to be around the rest of the day and tonight and tomorrow. So glad to talk with you as you would like. And also would say that these slides are all open, and we'll be glad to give you copies of them if you would like. So no need to take a lot of notes. And I have mostly slides from our customers and from folks at the Air Force Research Lab, and we'll use all of those and show you that quantum computing, in fact, even though it's early days, is real and is starting to get some traction now for real world problems. So without further ado, maybe we'll talk a little bit about some terminology. So first, quantum. What does quantum mean? Well, what it really means is sort of discrete levels, if you would. So you can think of the cupboard that you have in your kitchen where you store cans of soup and corned beef hash and stuff like that. I mean, that kind of is a representation of quantum. And so because there are different levels in that cupboard, and each of those is sort of like a discrete, in our case, energy level in the quantum world. But if you have a can of corned beef hash and you're going to put it in your cupboard, can you put it kind of between where those shelves are? Not really. You've got to put it on one of those discrete shelves, and you could think of those as each of them as a quantum level, if you would, or discrete, in our case, energy level. You can't put it in between the shelves. So that's kind of what quantum means, is discrete and quantized in the big picture. And then, of course, there's physics and mechanics and all the rest of that. But it means discrete sort of levels, if you will. And quantum is probabilistic. The universe is probabilistic. There's some chance that I'm appearing here from a different universe today. But probably not a great one, but there is some slight chance of that. And again, using the corned beef hash, when I actually put it in the cupboard and close the door, I put it on some shelf, and I leave and go do something else. When I come back, I have to try to remember which shelf I put it on. And so when I'm thinking about that, if I don't remember exactly, I think of it, well, I probably put it on the lowest shelf because that was the easiest one, but maybe I put it on the next one or maybe on the next one. Chances are kind of 90% that I put it on the lowest shelf, and 15%, I better use a smaller number, 7% on this one and 3% on the next one. So quantum stuff that we'll talk about is probabilistic. The big three terms that we all use in quantum computing and quantum devices and sensing are superposition, entanglement, and quantum tunneling. Superposition means that our bits, our quantum bits, qubits as we'll call them, are both a 0 and a 1 simultaneously. And we'll show you kind of what that looks like in a second. But back to our idea here with the corned beef hash, if in our cupboard, if we could put the corned beef hash in superposition with a can of Campbell's soup, this one can would be both things simultaneously in a state of superposition, and when we open the cupboard to get one out, it would become one or the other, because we're measuring it, if you will. Entanglement means that if I were able to, again, this isn't the physics description of entanglement, but if I were able to get these two cans of corned beef hash entangled, and they're both sitting, suppose I thought of them sitting upright as kind of a 1, and if they were upside down, that's a 0 position. If I can cause them to become entangled, and I keep one of the cans myself, and I put another can somewhere else, and I haven't looked at it, as soon as it gets turned over to a 0, mine also knows that. And now suppose that I'm able to take this corned beef hash can and launch it into space a couple of 100 miles, and it's still entangled with this one. On the ground or in space, I know when something's happened to my other entangled qubit or corned beef hash can. And that's what we'll talk about as we look a little bit about quantum communications and also intrusion detection. If somebody on the ground fiddles with the qubits, I'm going to know it in space or vice versa. So that's entanglement. And quantum tunneling we'll save for when we talk about how our computer actually works. And then the other thing you'll hear about with regard to quantum things is coherence or decoherence. And getting a computer into a quantum state is a bit of a challenge, as you'll see. And once you get it in that state, it's a little fragile. And so we measure the amount of time that you're able to keep it in this quantum state. We call that coherence. And the time that it falls out of it is the decoherence time. So that's a big deal. So those are some of the terms that you'll hear over and over and over again. We have great kind of nerdy clothes in the quantum world. And I actually do own a sport coat, and I own a couple of suits that I haven't gotten out for a while. But this is one of our superposition states. And so if you want shirts, and if you want to see about superposition, the famous thought experiment was by a German physicist, Schrödinger, like 80 years ago or something. And he said, if I put my cat in a box and there's something in there that might kill the cat or not, this was before the Society for the Prevention of Cruelty to Animals, said that, you know, when I just look at the box, I don't know if the cat is alive or dead. The cat is in a state of superposition. To me, it's both alive and dead, and I don't know which it is until I open the box. So you can look that up and see as you want. So we and everyone will use some of those terms. I'm going to show you a couple of slides from General Bill Cooley, who's the commander of the Air Force Research Labs. And he used these about a month ago at a conference where we were. And I thought they were great because they sort of showed the breadth of applications of things quantum. 3 big areas: sensors, communication, and then computing. And this is one which shows how the Air Force might be using in the future all 3 of those. So sensors to help you, for example, figure out in a GPS-denied environment, as we're all becoming prepared for, or starting to think about anyway. Can you use quantum devices to help do timekeeping and inertial guidance, for example, more accurate inertial guidance than you can do any other way? Theoretically, you can, and I think we'll see over the next few years. Quantum communication, to be able to send messages or information from air or space or sea back to terrestrial locations, and do it in a way that it is totally protected, and you can tell if someone's trying to intrude on it. And then also in the computing side. So to quantum compute, and so we won't talk anymore about quantum sensing and devices and quantum communication, but we'll switch now and talk about quantum computing. So Richard Feynman, the famous physicist, was the one who in 1982 really started talking about quantum computing. And maybe instead of designing digital computers to be able to simulate physics, maybe you could use physics, create a quantum computer to be able to do something useful to model nature. That was kind of his original idea. I first met him in 1983 at the time I was running computing at Los Alamos, and it was the 40th anniversary of Los Alamos. And Feynman gave so Don Kerr, who some of you would know, was the lab director then, and he said, let's get the band back together and have all of the folks who were here at Los Alamos in the 1940s come back, and we'll have a big to-do about it. And so Feynman was the kickoff speaker that morning, and his talk was the first time I'd ever heard of quantum computers. And you can see I've enlarged it: tiny computers obeying quantum mechanical laws. And a couple of days later, Feynman and others wanted to go for a tour of the modern computing at Los Alamos, and I'm standing, we were at the time the largest scientific and engineering computing facility in the world. And I'm standing in front of one of the crays saying, and this cray behind me can do 160 million calculations a second. And we have 5 of them. So imagine, with those and all these another long dead computer company, Control Data Corporation, 7600s and 6600s, we can do about 1 billion calculations a second. And Feynman said, young man, someday all of these big crays are going to be replaced by quantum computers. And I said something really remarkable like wow or cool, or I don't think we were up to awesome yet or any of those terms. But that was the first I'd ever heard of them. It took 35 years, but Los Alamos became our 3rd installed customer. So it's taken a long time, and we're just now really getting to the starting gate of quantum computing. When you build any computer, you need to pay attention to 2 things. One are and this is digital or quantum, the technology that you're going to use to implement it, and then secondly, the architecture of the computer. And so this was an article from Science from a couple of years ago that I thought was a good summary of the different types of technologies that you could use to implement a quantum computer, and there are others that people are working on now. Most of us are using superconducting loops, and I'll show you those in our case in a second. And you may have seen the IBM announcement earlier this week of their 20-qubit machine. And in fact, it uses superconducting loops as well. And there are many other technologies. And then on the architectural side, there are 2 big architectures that people are following today. So it's sort of like in traditional computing where 20 years ago when NVIDIA got started, there were CPUs of a variety of types, architectures, and then GPUs, and GPUs were a different architecture. The same thing true in quantum computing. The 2 big architectures are gate model quantum computers and then quantum annealing computers. The gate model quantum computers are like what IBM is doing. This is a slide from our friends in Germany at the National Laboratory at Jülich. And basically, the gate model machines operate sort of like you would think of a digital computer, in that you connect a series of gates to cause some function to be performed. On your cell phone or your laptop, a circuit designer has created an adder in your computer, and you just give it numbers and it adds them, and it is created by a circuit designer connecting a bunch of AND gates and OR gates and shifts and those sorts of things. Similar idea here, except you become the circuit designer. You have a handful of gates, you connect them, and the idea here is this is a 5-qubit version. Lines Q1 through Q4 are the 5 qubits in this machine, and then you can see sort of as it goes across horizontally that different things are happening at different points in time, and you can sort of think of those points in time as you go across horizontally as equivalent to a clock cycle in a digital computer. And during that whole calculation, the machine really needs to stay in the quantum state, and you need to not have errors for the result of the calculation to be correct. So that's sort of how gate model machines are all following that sort of path. The quantum annealing architecture is really weird and different than anything that you've used before, and this is sort of our circuit diagram for quantum annealing. And our quantum annealing machine doesn't add numbers or subtract or multiply, but what it does is that if you have a problem that you can map onto an energy landscape, it will find the lowest valley or valleys in that energy landscape, probably. Probabilistic, remember? So if you have a problem that looks like these are the Beartooth Mountains up near where I live, and you can map that onto this machine. It's really, again, an energy landscape, and it's n-dimensional rather than 3 dimensions. But what it does is it finds the equivalent of the lowest valley. What it's really doing is collapsing to a low energy state, and then you read out, you get the results of what is the equivalent of the lowest valley. And if the energy landscape is steep and rugged like this, and you run it 1,000 times, there might be 911 answers in the one low valley, and 13 in another, and 7 in another. So you'll get a distribution of answers. If your problem is like the Sahara Desert, you'll get answers all over the place. So unlike our deterministic digital computing, the answers you get are dependent upon the problem that you have in this case. So it, again, is quite different. DWave is one of the world's longest running startups, was founded about 20 years ago. And we have systems installed at Lockheed, Google, Los Alamos. Oak Ridge is using 20% of one of our machines. And those folks have about 50 others. And then we have today actually about 40 industrial cloud customers. And to purists, it's more remote batch is what we used to call it, but we'll call it cloud today. And people can access our systems through AWS and other mechanisms as well. This is what they look like. These are 2 systems. They come in a giant box that those in the classified world would call a skiff. And the idea is that that big box is a Faraday cage, and it keeps out radio frequency interference. And if we walked inside, we would see a giant soup can, or today, I guess, a giant can of corned beef hash. And if we took that one off, there's another one, and another, and another, and each of those are layers of shielding. And they stack sort of like the Russian dolls stacked together. And if we took them all off, we'd see sort of the Terminator's arm there. And at the very bottom of it is where the actual computer is. And it starts off at room temperature, and then liquid nitrogen temperature, all the way down to where the processor is. It's 10 to 15 millikelvin. So it's very, very cold, much colder than outer space, as Terry will tell us in a little bit. But we have to protect it that way because this quantum environment is fragile. So we do lots of things to protect that, but at the very bottom of that, the quantum computer is 1 chip, and it's about the size of your thumbnail, and that's what our 2,000 qubit version looks like. And basically, to program it, you give values for the qubits and the interactions between the qubits. That creates this energy landscape. And then the machine, without adding or subtracting, goes to a low energy state, sort of the equivalent of finding a low valley. So With that in mind, we've been, Moore's law is dead, probably not really. Moore's law is going to continue, but the slope has certainly changed. We've been fortunate enough to be able to, every couple of years, roughly double the number of qubits that we have in our machines. We're 2,000 today, passing through that to about 5,000 in the next iteration, which should be a year and a half from now, or maybe a little bit less than that. So what have people done on the machines? So this is, and I'm going to go through this part very, very quickly, and again, you can all have it if you would like. But there are about 100 proto-apps, as I call them, or early applications running on our machines, all pointing toward real-world applications generally. About half of them are optimization, about 20% AI and machine learning, and then just starting to get into material science. In about half of them, the performance or the quality of answer is at or approaching that of conventional computers, but always for small problems. We can't do big problems yet, but techniques to decompose them are coming along. These are the early system customers, at least the unclassified early system customers, and these are what they're doing on them. I won't read this to you, but rather we'll show you some of the things they're doing, and these are some of the cloud customers and work they're doing. And again, I'll try to more show you what's happening. This is a slide from NASA's partner USRA, who's sort of the university outreach part. And this just shows you some of the organizations who are using the NASA Google machine through USRA. And then the same thing with Oak Ridge and some of their partners who are working on projects in these early applications. So you would recognize almost all of these names, including our friends from Total, working with Oak Ridge and ourselves. The first early application on a quantum computer that you could explain to your parents or someone in the supermarket was what Volkswagen did. So about 2 years ago, the Volkswagen CIO called me up and said, "Bo, I'm going to be in Silicon Valley here in a couple of months, and we're hearing a lot about quantum computing. Would love to hear what's going on." So we said, "Great, we'll meet you." And it all went great. They were very interested. And at the end, he said, and these are now just about everything I'm going to show from here are slides from customers. And so what he said was, is there a real world problem we could do with the DWave machine? And we said, well, there are a collection of them, we think. So he said, how about traffic flow optimization? Let's see if we can't, an optimization problem, sort of like finding a low valley in this space. And let's start with taxi cabs in Beijing. We, Volkswagen, have the GPS coordinates of 10,000 taxis in Beijing every 5 seconds. And this is a sort of a Google heat map of what the congestion looks like. And so let's solve that problem. How Volkswagen has the GPS coordinates of 10,000 taxis in Beijing every 5 seconds is not for me to know, I think, but they have it. And so we said, wow, great problem, but way too big for what we can do today. But maybe we can break it down. And so we started with, said, let's look at from downtown Beijing, which is in the lower left of the picture on the left, to the airport. And you can actually see the runway. Maybe you can see the runways in the upper right. And that's, again, about 500 taxis en route. And so then the hard part started, how to figure out how to take this time-dependent GPS coordinate data and create this energy landscape from it. And that took 3 months. So a lot of work, smart people involved, but they figured out how to do it. And then when they ran it in a second or two, we'll get 5,000 good solutions to it. And we may get some bad ones, but you really probably have the best solution to it. And the picture on the right is the result of that. And so every couple of seconds, you can get a new solution based on where the taxis now have moved to. So that was kind of cool, and it got a lot of press and a lot of notoriety, and it also sort of started to create a recipe that others could follow to be able to figure out how to do that. Then our friends at Booz Allen Hamilton said, taxis are kind of cool. Don't know about Beijing, but that's kind of cool. But what about an important problem like optimizing a constellation of satellites? You have priority targets. You want to minimize the slewing. What about that? Can you do that? And so we worked with them. Took about 3 months to figure out how to map that onto the machine. And sure enough, you could. And again, these are their slides. And what you would see here is characteristic of what everybody's found. Most everybody's found that, in fact, machine, once you figure out how to map your problem onto it, it works. And in some cases, getting results that are comparable to traditional computers, but always for small problems. And then our friends at DLR, the German Aerospace Agency, said, well, what about taxis satellite's important, but what about something really important like air traffic routes over the North Atlantic? Can we help optimize those? Did some work. Sure enough, you could do that. We can't do all of them yet, but we have a start to be able to. And then other friends in Japan at Recruit Communications said, cool, but what about an important problem like optimizing the placement of internet ads on a cell phone to maximize the click-through rate? Don't know how to do that. We and they figured out how to do it. And the results were they got a little better click-through rates using the optimization package from the DWave than they did using their traditional mathematic technique. Others in Japan at Tohoku University, huge tsunami 8 years ago, I guess, in Sendai, killed 20,000 people. Japanese national project now to see if you can use our machines to help optimize getting people out of the way of natural disasters, but the tsunami in particular. I wouldn't be surprised that our first machine installed in Japan goes to Tohoku. Then in the UK at British Telecom, looking at some very complicated problems about how do you route traffic and find intrusion. And the results here are the same. These, again, are British Telecom slides that we get good answers very quickly and need bigger problems. Ocado, also in the UK, is the world's largest online supermarket that you've never heard of. And what they've done is they've created these warehouses where they have thousands of bins of groceries and hundreds of robots that run around on these orthogonal rails. And the idea is within 15 minutes of you submitting your order for groceries, they want to have your groceries picked and ready for delivery. Huge optimization problem. So the results of that were that it works, and we're moving on to the next things. Now moving to machine learning here for a couple of minutes, and then we'll wrap up. There's a fellow who was at Stanford Research Institute in Menlo Park, a medical doctor, but really quite an accomplished computer guy. And he said, in today's world, we have more information about you than we've ever had. But some of it's conflicting, and we have a hard time coming up with diagnoses and recommending what you should have. Maybe we could create a map, a graph, of each person individually, and maybe we could use the quantum computer to be able to fill in some of the things that we don't know probabilistically. So we worked with him. He became convinced and liked this idea, and he has now left his well-paying day job at SRI and has created a startup to pursue this. So he's off and running. And in one of the weirdest things, a young fellow at a company in Washington said, I'm going to see if I can't create a model on the DWave to look at the last US presidential election where most of the polls said that Donald Trump had no chance, but somehow he did. He won. And so I'm going to just see if I could do it. And surprisingly, the model that this fellow created on the DWave actually and he took snapshots right up to the election of every 2 weeks. So this was after the election. But what it predicted was that Trump had like a 40+% chance of winning, which was quite a bit more. And what turned out was that there are correlations in the data that the traditional mechanisms didn't see. And there were these relationships. So, and again, you can look at all these. Material Science, a startup company in Toronto called OTI, who are designing organic LEDs as are used in your cell phones and televisions. They're moving up the curve. We're getting closer to be able to do industrial strength molecules on our machines. And then this is sort of one in the cyber world, some folks at Los Alamos. This is seeing if the friend of my friend, creating a linkage of cell phones or networks, and seeing sort of the problem is the friend of my friend, so the friend of my friend is my friend, but is the enemy of my enemy my friend, and what are the linkages that are out there that I don't know? And can you try to predict what's going on? We're getting closer to having 3 applications, I think, in the next year that might be used in production. One of those is our friends from Recruit, who run Japan's largest hotel recommendation service. And so you say, I want a hotel on the Marunouchi side of Tokyo Central Station within 3 blocks and 5 blocks from a Greek restaurant. Well, so they've tried it. They ran the DWave side by side with their traditional thing for 6 weeks and increased their revenue by about 1% using the recommendations from this. It's a bounded problem. There aren't thousands of hotels in that that meet that criteria. My friend Martin Hoffman from Volkswagen, the CIO of Volkswagen Group, we gave a talk in Lisbon at one of these big Web Summit conferences about 2 months ago. He said next year, when you come to Web Summit in Lisbon, you'll be able to download an application where in the back end of it, DWave will give you an optimized route from wherever you are to somewhere else, given the location of taxis, Ubers, buses, and all of those sorts of things. And then Denso, with autonomously guided vehicles within a factory, has an application that is trying to automate the flow of those. Videos here that you can look up. And they have, using our machine, have found about a 15% better routing to minimize the congestion caused at the intersections. So I think those three are pointing toward real-world application. Quantum computing has also moved so far along that we're now in fiction. So Dan Brown's book started with a D-Wave. The D-Wave wasn't good enough, so he invented an E-Wave to be able to help. And then David Ignatius, who I'm sure some of you know, Quantum Spy was great. There's also been a TV show. And one of the other characters from Big Bang, we've been really trying to get Sheldon in particular to wear one of our t-shirts, but we haven't succeeded at that yet. So with that, all of this stuff is available, also information at these websites with presentations about just about everything that the customers have done. So early days of quantum computing, we're really just at the starting line now, but it's real, and it's going to play a much bigger role in your lives in sensors and in communications, and in our part in computing. So with that, I would say thank you very much. That's the, I shouldn't forget to take my corned beef hash, or someone's, and would say thanks. And I don't know if we have time for a question or two. We'll call her good. Thank you.
All right. The next two distinguished guests are going to be joining me here in a minute, taking their seats, and